Okay, so you fold your first paper airplane and fly it across the room. You're happy it works, but then you remember the wings of your paper airplane are flat. Obviously, it's made of paper. But aren't wings supposed to look like teardrops to work? No, not necessarily. So what's going on? Imagine you're a happy little wing minding your own business. But the pilot fires up the engine and now you're staring down a bunch of air molecules rushing straight towards you. You do your best to push back and push down so they move past you. This arrow represents you pushing back, and this one pushing down. Well, these annoying buggers aren't going down easy, and they retaliate in accordance with Newton's third law of motion, which stipulates that for a reaction, there's an equal and opposite reaction. So these guys push back and up at you in the same magnitude but in opposite directions. Let's move these arrows so it's easier to see. The arrow pointing back is drag, and drag slows down the airplane. The arrow pointing up is, you guessed it, lift, and lift is what makes flight possible. The same happens when you get bored driving and stick your hand outside your window. When your hand is horizontal with the ground, not much happens, but when you angle it up, you can feel your hand being pushed up and back. It's the same principle at work. In reality, wings don't have to look like teardrops to work. In fact, there are numerous designs out there, including flat ones used for supersonic flight. So why do most wings look like teardrops? It's because engineers want to direct air above and below the wings in a specific way to suit their needs. When air molecules hit the wing, there's a point on the wing where air separates, one group going up, another down. This is called the stagnation point. Air molecules arriving above the stagnation point will be redirected tangent to the convex curve of the upper part of the wing. But that will create a vacuum between the air molecules and the surface of the wing, pulling them back. This is called the Coanda Effect, and this is why air molecules above the wing follow the wing's convex curvature. And by doing so, air molecules above the wing are directed or pulled down by the wing. In response to this downward pull, an equal and opposite reaction by the air molecules pull the wings up. So the third law of motion acts to create lift not only below the wing, but above it as well. And that's how wings work to create lift. Stick science. Thank you for watching. If you didn't already know, Newton's third law of motion isn't the only way to explain lift. An equally valid method is by using the Bernoulli's Principle, which gets a bad rap because of the equal transit time fallacy. Our next video will explain lift using Bernoulli's Principle, so please subscribe if you don't want to miss out.